In this section 8.2, we want to take a look at what we call a series. But before we just jump into doing some problems, I want to look at a definition, and then we'll look at some notation. Here's a definition I got from the Webster's Dictionary. A series is the indicated sum of a sequence of numbers. Here's an example. Here's a sequence of numbers. What if I have 3, 5, 7, 9, 11. There's a short sequence of numbers. Now, if I want the corresponding series, I would take out the commas and replace it with plus signs. So 3 plus 5 plus 7 plus 9 plus 11. That's a series. Now, it's sometimes, or most usually, awkward to write everything out like this. So what we're going to do instead is this. We take that word series, and series starts with a capital S. So what we're going to do is use a capital Greek letter sigma. All right, this right here is the Greek letter sigma to indicate that we have a series coming up that we want to sum whatever it is we're going to write over here. Here's an example of a series. I'm going to write, there's the Greek letter sigma, but right below and above it, I'm going to write this. I equals, say, 1 to 4 of something like this. Maybe I'll write 3i plus 2. This lowercase letter I, this is called the index. And in this case, what I mean by an index is it's just something that's used to point something out, to indicate something, to name something. Now, you can see here that I equals 1. All right, now the bottom number here, this is called the initial value. That's where I starts. So in this case, I starts at 1, and then it goes consecutively through the integers. 1, 2, 3, and then it terminates right here. We have to tell it where to start, where to stop. So this is, say, the terminal value. And apparently I can't spell terminal. So that is the terminal value. And this right here, this 3i plus 2, that's the general term of a sequence. Let's expand this. All right, we'll expand this and see exactly how to work this. So first of all, I'm going to start with I equals 1. All right, now I'll write each term here separately. When I is equal to 1, what do we get? So just come back up here into your general term and replace all the i's with the start value with 1. So it looks like 3 times 1 plus 2, which is what? 3 plus 2, so we get a 5. When I is equal to 2, we'll get 3 times 2, right? Now where'd that come from? Well, you start at the initial value and then you increase I consecutively through the integers. So I start at 1, then I go to 2. Now replace that I with a 2. So 3 times 2 plus 2. So I get 6 plus 2. So I end up with 8. When I is equal to 3, we're going to get 3 times 3, right? And that 3 right there is coming from I equals 3, and I put it right here. 3 times, okay, it's the third value of I, 3, plus 2, so that's going to be 9 plus 2, which is 11. And then we get I equals 4, so we'll get 3.4 plus 2. Looks like 12 plus 2, so I end up with 14. So we've generated the sequence, which is 5, 8, 11, and 14. But what's happening is that we want to sum. If you come down here, right, this sigma is the first letter of the word series, but it's also the first letter in the word sum. So what I want to do is find the sum of these terms, and that's what this definition is. It's the indicated sum. There's the indication. This indicates take the sum of these terms, right? So what I would write then is this. I would write 5 plus 8 plus 11 plus 14. We can actually add those together. So what do we get here? I think we get 38. Now just go back to look at this back here. I want to look at these i's. This I, that's going to be the term number. So I equals 1. This is the first term in our sequence. Turned out to be a 5. The second term in the sequence is 8. The third term. So the I, that just tells you what term in the sequence you're at. So what we have down here, I'll draw it down here. That was the first term in the sequence. That's the second term. That's the third term. And that's the fourth term. And if we look at this definition up here of the sequence, can you see what this tells us? It says what? That the value of the term, like 5, the value of the term is always what? 2 more than 3 times the term number, right? So it's 3 times the term number and 2 more. So if you want to know what value it is, here's the term number. It's 3 times that and 2 more. Then you come over here. 2 more than 3 times the term number. 3 times the term number, well, it's term 2, so that would be 6, and 2 more, and so on. So what would the next one be if we had another one? Well, the next one would be term number 5, and 3 times 5 is 15, and 2 more, 17. Let's do another real short one here. What if we had this? The summation, say I equals, say 4 to 5 of something that now looks like this. Say it's x to the I plus 1 plus 3i. Now I'm using the index to be I. By the way, it doesn't have to be I. We just choose I because it matches the word index. But in your work, you could use any letter you like. I, J, K, those are common. So this one tells me my initial value is 4. So I'm starting, say, at the 4th term. And what do I do to expand this? I want to expand this. So I'm going to start with I equals 4. And everywhere I see an I, I'll put a 4. So when I is equal to 4, I'm going to get this. I'm going to get x to the 4 plus 1 plus 3 times 4. Okay, there's the first term in this series. Plus, right now, why is it a plus? Because of that. That's an indicated sum. It tells me to take that term, add it. All right, so the next term, that's why I stopped at 5 so we wouldn't get carried away. X to the, now, I started at 4. Increase it by 1 to 5 and replace that I. So it's now 5 plus 1 plus 3 times 5. We can simplify a little bit, right? What do we get here? We'll get x to the 5th plus 12 plus x to the 6th plus 15. I can do a little bit. I can combine those. So how about this? And I'll write in descending order of the exponents. X, well, how about just x to the 5th plus x to the 6th plus 27. So that's what we need to know about this notation. Now we'll just start working some of the homework problems.